Okay, here we have section 8.5, actually solving problems involving vectors, so these will be word problems. So objectives, solve problems using vectors, and then perhaps some right-angle trigonometry. Now, just as a general rule, when you're working with vectors, regardless of how the problem's set up, your first step should always be to turn them into their components, the x and the y values first, so the horizontal and vertical components. So example 1 here, a bull rider has completed his competition ride and 2 rodeo clowns are restraining the bull to return it to the paddocks. One clown is exerting a force of 270 newtons due north, so we'll draw that. So there's 270 newtons pointing north. The other is pulling with a force of 360 due east. What is the resultant force on the bull? So we have two forces, the 270 force and the 360 force. So kind of do this in the table, 270 and the 360. So the 270 degree force is acting at 90 degrees, so I'll put it in parentheses, and the 360 Newton force is acting at 0 degrees. So the horizontal components and the vertical components. So to find horizontal, you take your magnitude times the cosine of the angle. So 270 times the cosine of 90 will actually give you 0. 360 times the cosine of 0 will give you 360. Over here, this is times the sine of the angle, 270 and 0. And then you can sum these up to get the resultant vector. So 360, comma, 270 is the resultant vector. So what is the resultant force on the bull? So resultant force, force is measuring the magnitude of this vector. So to find the magnitude, you take the square root of the sum of the squares of your components. So 360 squared plus 270 squared, take the square root. So they're applying a total force of 450 newtons to the bull. Okay. Now if you're to calculate work, you're multiplying the force vector and the distance vector. And you need to find once again the components before doing this. So Alvaro works for a package delivery service. Suppose he is pushing a cart full of packages weighing 1,000 pounds up a ramp 8 feet long at an angle of 25 degrees. Find the work done by gravity as the cart moves the length of the ramp. Assume friction is not a factor. So kind of sketch a picture here. So there's a force of 100 pounds pulling straight down. The ramp forms an angle of 25 degrees, and the ramp is 8 feet long. So it wants to know the amount of work. So that's the 8. What we actually need to do is figure out how much, there's actually an easier way to do this problem. Work is equal to force times distance. So, but it's the force in the direction you're pushing. So the amount of the 100 pounds of the weight that's actually acting along the ramp. So you kind of have to drop a triangle like this. The right angle goes there. This angle up here is also 25 degrees. So that means this side here is the sine. So it's the weight times the sine of 25 degrees. So my force is the magnitude times the sine of the angle. So 100 sine 25 is a force of 42.3 newtons. And that's actually what I can plug into this equation. So 42.3 times 8 . So 338.4. Newtons of work. Okay, final example here. So Ms. Davis is hanging a sign for a restaurant. The sign is supported by 2 lightweight support bars. The bars make a 30-degree angle with each other. And the sign weighs 200 pounds. What are the magnitudes of the forces exerted by the sign on each support bar. So you're hanging a sign. Looks like this. So there's your sign. This angle is 30 degrees between the two of them. The sign weighs 200 pounds. So that means these support rods have to hold 200 pounds. So there's some imaginary arrow pointing up here that's 200 pounds. Since there's two of them, each side of this triangle, in which that's 15 degrees, has to hold 100 of the pounds. And you're looking for the force on each bar, so how much the hypotenuse in this case is holding. So you know the adjacent side, you're looking for the hypotenuse, that's cosine. The cosine of 15 equals the adjacent side over the hypotenuse. And then you have to solve for x. So each bar is actually holding 103.5 pounds of force.